You are floating 310 miles from the point of no return. Behind you, stars bent into smears. Below you, a circle of absolute nothing. Not darkness, not emptiness, nothing. A hole in the fabric of reality itself. And you're about to fall in. Now, spoiler alert, you don't make it. Not even close. But the how is where things get interesting, because a black hole doesn't just end you. It stretches you, freezes you, duplicates you, and possibly deletes you from the universe all at the same time. So let's jump in, literally. Before we destroy you, let's talk about what's waiting down there. A black hole is what happens when a massive star, we're talking 20, 30, sometimes 50 times the mass of our sun, runs out of fuel and its core collapses. Imagine a star the size of a city being crushed into something smaller than an atom. All that mass, all that gravity, squeezed into a point with zero size and infinite density. Physicists call that point a singularity. I call it the universe's most dramatic overreaction. Around this singularity is the event horizon, an invisible boundary where the escape velocity exceeds the speed of light. Cross it, and you can't come back. Not because of a wall, not because of some force field, because space itself is falling inward faster than light can travel outward. Every possible direction you could move, left, right, up, down, all of them now point toward the center. It's like trying to swim upstream in a river that's moving faster than you can physically swim. Except the river is space, and the waterfall is a singularity. And you forgot your floaties. Okay, you're in your spacesuit, approaching a stellar mass black hole, about 10 times the mass of our sun. You chose a small one. Bold move, terrible decision. Let's see why. The first thing you notice is the sky doing something deeply wrong. Stars behind the black hole aren't hidden. They're bent around it. Light from behind curves so hard it wraps around the edges, creating a glowing halo. You can literally see the back of the universe reflected around this thing. This is gravitational lensing. The black hole's gravity is so extreme that it bends the path of photons like a cosmic funhouse mirror. And it's beautiful, terrifyingly, hauntingly beautiful. As you get closer, the entire sky behind you begins to compress into a tiny, bright circle. Everything you've ever known, the sun, Earth, the galaxy, squeezed into a shrinking dot of light above your head. Meanwhile, the darkness ahead grows and grows until it fills your entire field of vision. It's the last sunset you'll ever see, and it's everywhere. Now here's where it gets properly weird, because what happens to you depends on who's watching. Let's say your friend stayed behind on a space station at a safe distance. They're watching you fall in through a very powerful telescope, probably eating popcorn, probably judging your life choices. From your perspective, you cross the event horizon and nothing special happens. Seriously, there's no wall, no membrane, no dramatic flash. You don't feel a threshold. The event horizon isn't a place. It's a point of no return that you only recognize in retrospect. Like texting your ex at 2 a.m. By the time you realize what you've done, it's already too late. But from your friend's perspective, they never see you cross. As you approach the event horizon, your image slows down. Your movements become sluggish. The light reflecting off your suit gets redder and dimmer. Gravitational redshift stretching the wavelengths until you fade from visible light into infrared, then into microwave, then into nothing. To your friend, you freeze at the edge, a ghostly image of you getting dimmer and dimmer for potentially millions of years. They'd grow old. Their entire civilization could rise and fall, and your image would still be there, a fading smudge on the edge of darkness. You've become a permanent postcard from the edge of space-time. You're welcome. This is time dilation, Einstein's general relativity in action. Near a black hole, gravity warps time itself. The closer you get, the slower your clock ticks relative to someone far away. At the event horizon, that ratio goes to infinity. All right, from your perspective, you've crossed the event horizon. You're inside the black hole now, and this is where the ride gets bumpy. Here's the thing about gravity near a black hole. It's not uniform. The gravity pulling on your feet, which are closer to the singularity, is significantly stronger than the gravity pulling on your head. This difference is called tidal force, and near a stellar mass black hole, the difference is enormous. Your feet accelerate faster than your head. You begin to stretch. Vertically, you're being pulled apart like taffy. Horizontally, you're being squeezed because the tidal forces also compress you sideways as everything converges toward that central point. This is spaghettification. And yes, that is the actual scientific term. Physicists decided that the process of a human being ripped apart atom by gravitational tidal forces deserved to be named after pasta. And honestly, respect for a stellar mass black hole, say 10 solar masses. Spaghettification happens before you even reach the event horizon. You'd be torn apart around 435 miles from the center. That's roughly the distance from New York to Pittsburgh, except instead of a road trip, it's the last stretch of your life, literally. But here's a twist that'll keep you up at night. For a supermassive black hole like the 4 million solar mass monster at the center of our galaxy, Sagittarius A, the event horizon is so large that the tidal forces at the boundary are gentle, almost unnoticeable. You could cross the event horizon of a supermassive black hole and feel absolutely nothing. You'd only realize something was wrong when it was far, far too late. You'd be inside the prison before you even notice the door. And that might be the scariest part. Not the violence, the silence. So what happens when you actually hit the center? The singularity? The bottom of the rabbit hole? Honestly, we don't know. And I don't mean we don't know yet. Give us a few years. I mean our best mathematical models literally break down. The equations of general relativity produce infinities. Infinite density, infinite curvature, infinite... You've got to be kidding me. When your math gives you infinity as an answer, that doesn't mean the thing is actually infinite. It means your math has stopped working. It's like asking a calculator to divide by 0. The calculator doesn't give you a wrong answer. It just gives up. That's what general relativity does at the singularity. It gives up. To figure out what actually happens there, we'd need a theory of quantum gravity, a framework that unites the physics of the very large with the physics of the very small. We don't have that theory yet. It's the holy grail of modern physics. And until someone finds it, the singularity remains the universe's most expensive Error 404 page. But, and this is a big but, a 2025 study from the University of Sheffield proposed something wild. Using a modified version of quantum mechanics called unimodular gravity, researchers showed that the singularity might not be a dead end at all. Instead, it could be a transition, a bouncing point where a black hole becomes a white hole, ejecting matter, energy, and time back into the universe. So falling into a black hole might not be an ending. It might be the weirdest beginning in the universe. But don't pack your bags. This is still firmly in the wild speculation category. Beautiful speculation, but speculation. Okay, so you've been stretched, frozen, and possibly ejected through a white hole. But there's one more problem. And this one doesn't just affect you. It threatens the fundamental laws of physics. It's called the black hole information paradox, and it's been keeping physicists up at night for 50 years. In the 1970s, Stephen Hawking showed that black holes aren't completely black. They slowly emit a faint glow of radiation, now called Hawking radiation, and over unimaginably long time scales, this radiation causes the black hole to shrink and eventually evaporate completely. But here's the problem. According to Hawking's original calculation, the radiation that comes out is random, thermal noise. It contains no information about what fell in. So when the black hole finally evaporates, poof! all the information about everything it ever swallowed is just gone. And that violates one of the most sacred rules of quantum mechanics. Information can never be destroyed, ever. You can burn a book, but technically, theoretically, and if you tracked every single ash particle and photon, you could reconstruct the book. The universe keeps receipts. But if a black hole can delete information, the universe just lost your save file permanently. This paradox sparked one of the biggest debates in the history of physics. Hawking said information is lost. Nearly every other physicist said no way. They argued for decades. Hawking eventually changed his mind and conceded the bet in 2004, admitting information probably is preserved. But we still don't fully understand how. Recent breakthroughs, including the discovery of so-called entanglement islands inside black holes, suggest that the information is encoded in subtle correlations within the Hawking radiation. The math now shows that information slowly leaks back out as the black hole evaporates. It's not lost. It's just really, really well hidden. Like finding your keys in the last pocket you check, except the keys are your atoms and the pocket is a fading black hole. So here's the thing. We just spent 13 minutes talking about the most violent, extreme, reality-breaking objects in the universe, and you'd think that would make you feel small, insignificant, a speck of dust next to a cosmic drain. But think about what we actually just did. We, a species that has existed for about 300,000 years on a medium-sized rock orbiting an average star, we figured out what happens inside an object where the laws of physics break down. We can't go there. We can't see inside. We can't survive the trip. But through mathematics and imagination and sheer, stubborn curiosity, we know what the inside of a black hole does to space-time. We know how light bends around it. We know how time warps near it. We even know it slowly evaporates. We named the process of being torn apart by gravity after pasta. We argued for 50 years about whether the universe keeps receipts. We built telescopes that captured the literal shadow of a black hole 55 million light years away. A black hole is the universe at its most extreme, and we, fragile, squishy, pasta-naming primates, stared into it and said, "Explain yourself." That's not insignificance. That's the most impressive thing any collection of atoms has ever done. So, what happens if you fall into a black hole? You get stretched into spaghetti by tidal forces. You freeze as a ghostly image at the event horizon from your friend's perspective. You cross into a region where every direction leads to the center. You possibly hit a singularity that we can't describe with current physics. Your information might leak out over billions of years in the faintest radiation the universe has ever produced. And somewhere, 50 years from now, some physicist in a lab coat will probably figure out exactly where your atoms went, because that's what we do. We don't stop asking. The universe doesn't owe us answers, but we keep taking them anyway. If this video made you slightly more afraid of space and slightly more proud to be human, subscribe. We do this every week. Next time, we're looking at something that could delete reality itself. No black hole required.